Okay, hi everybody. I am now going to go through the solution for problem 75 from chapter 9. And this is a problem we've seen before, and this is a really great example, so you should be excited about this problem because we are now ready to fully model this system. When we solved this problem first in chapter 4, we ignored friction and we ignored the massive pulley. Later on in the class, in chapter 5, we learned about friction. And we did this problem again, now taking into account the fact that object A sliding on this table could be experiencing friction. And now that we've learned about rotation, we can now fully model the system. We can take into account both the gravitational effect on this object B, which is falling. We can take into account the fact that this pulley has mass and has some moment of inertia, and it's going to take some torque to turn it. It's going to have some kinetic energy once it starts turning, and we can take into account the friction in this as object A moves across the table. So fully modeling it is going to take a little work. It's going to be a somewhat long problem, but it's really worth doing because we've done this in lab. We can now fully make predictions in lab, and you can go back and see your results in the lab, and maybe you didn't take into account the pulley in lab, and now you know how to do that. Now you can take into account something that you had ignored before. So we can really model the system better now. Okay, so we have a tabletop. We have object A on top of the table. And I'm again sorry, my printer is not very good, but I think the picture is relatively clear. Object A is pulled by the string, so object A is going to start sliding in this direction. The string is wrapped around this pulley. The pulley has some mass, and that string then is attached to this object B, which is just held up by that string. So B is going to start falling. It's going to cause this pulley to spin, and it's going to pull on A. Okay, so we have to fully model this system and come up with an equation to predict the velocity of B after it's fallen some distance d, after it has descended d, some distance. So there's no numbers in this problem, it's just deriving the equation that we can use to predict the velocity of object B. Okay, so a really nice problem. And in general, you should solve problems in this way anyway. You should derive an equation for your final answer and then plug in your numbers. So, okay, how are we going to do this? It suggests we use energy methods to solve it, so let's try that. And let's see. We need to think about what energy the system has initially at time 1. We need to think about what energy the system has at time 2 after everything has started moving. And we need to think about how much energy is lost due to friction, right? There is friction on the tabletop, so we need to take that into account. Our goal is to use our conservation of energy equation, but the one where energy is not conserved, right? The total energy at time 1, whatever we define to be time 1, we're going to define it to be before anything starts moving, plus whatever work is done by friction, which either, in this case, is going to take energy out of the system. This is going to be some negative number of joules, gives us our final total energy, right? So this is our goal. We need to figure out what E1 is, what the work done by friction is, and what E2 is. So let's start by figuring out what the work done by friction is. The friction is only going to affect object A. I can draw a free body diagram for A. I've got a normal force. I've got the weight of A. I've got a tension force in that string. And it's going to be moving, so I have some kind of a kinetic friction, which is resisting the movement of A. Okay? And we know that we have an equation for the force of friction. This is one of the equations on your equation sheet. The force of friction is equal to the coefficient of kinetic friction times the normal force. Okay. From this free body diagram, I can recognize that in the y direction, the sum of the forces has to be 0 because it's not moving in y. I have two forces in y. I have the normal force in the plus y direction, right, and I have the weight in the minus y direction. Right, so that means that the normal force must just be equal to the weight of object A or equal to the mass of A times g. Okay, so now I know what the friction is. Replace n with my normal force. Okay, so how much work is done by friction? Okay, we have an equation for work, and in the case of a constant force, in one dimension, it's really a simple formula. So the work done by friction is just going to be equal to the force times the distance, right? In this case, the force is minus F of k, right? Because the displacement is in what I'm calling the plus x direction, but the force is in the minus x direction. So I have a negative force times its displacement is just delta x. That's how far it's traveling along the table, okay? And so the work done by friction is therefore minus, I can plug in my equation for friction, minus mu k mag. And then for how far is it going to travel, I know that b is descending a distance of d, little d. So if b is falling the distance of little d, that means a must be traveling along the table a distance of little d. So that is my equation. This tells me how much energy is going to be lost due to friction. This is the work done by friction. It's energy that's leaving the system, right? So energy is not going to be conserved. I start with some amount of energy. This is how much energy is going to be leaving, and this is how much energy I'm going to finish with at the end. Okay, so I've taken friction into account. Now I have to take into account the other types of energy. So to define my total energy at time 1, well, A is not moving at that rest, B is not moving at that rest, and our pulley is not moving at time 1, so there's no kinetic energy initially. Whether there's potential energy or not depends on my choice of coordinate system. All right, so I'm just going to define this to be y equals 0. Right? That means that the potential energy of object B at time 1, which is equal to the mass of B times g times y, is just going to be equal to 0, right? Because I defined it to be at position of y equals 0 at time 1. You could have chosen something else, and that would have been totally fine. I'm just making that decision, okay? And you'll note that at time 2 is when B has now descended some amount of distance, and it is down here, and it is now fallen some distance, and its final position is y is equal to minus d, right? Because I've defined plus y to be upwards. So it's fallen a distance of minus d. So the final potential energy of object B is going to be mbg minus d, right? Or minus mbgd. Okay, so that's just how I've chosen to set up the problem. There's many ways you could have done this. But that's just one of the types of energy we have to deal with. So let's now fully define this problem. Okay, what is the total energy at time 1? Well, I've written it in such a way that the total energy is 0. The kinetic energy plus the potential energy at time 1, nothing is moving, so nothing has kinetic energy, and I've defined my coordinate system so that object B has no potential energy at time 1. A is not going to be traveling in the y direction at all, so its potential energy is not going to be changing. We don't have to worry about its potential energy. So I've defined it so that the total energy at time 1 is just equal to 0. Okay. Total energy at time 2 is where the fun part of this problem begins, which is I need to think about all the types of energy that are happening at time 2. All right, so at time 2 is when B has now descended and B is moving, A is moving, and the pulley is now spinning. Okay, so at time 2, I have the kinetic energy of object A, right? That's 1/2 the mass of A times the velocity of A squared, plus the kinetic energy of B, which is now moving. Right, so that's 1/2 the mass of B times the velocity of B squared. This is what we would have done in chapter 6 or 7 when we were solving this problem using energy methods. But now we know that there's other kinds of energy here. The pulley is going to be spinning. Right? The pulley has mass. It has a moment of inertia. If it's spinning, it's going to have rotational kinetic energy. So I need to take that into account now. That's our equation for rotational kinetic energy, 1/2 the moment of inertia times the angular velocity squared. And then the final type of energy I have at time 2 is the potential energy, which I've already defined up here. Right? That's minus mbgd. Okay? So at time 1 we have no energy. At time 2 we have 3 types of positive energy and 1 type of negative energy. Okay? And then putting it all together, we can use our original equation. Whatever energy we start with, minus whatever energy is leaving the system, leaves us with whatever energy we're finishing with. Okay, so let's do that. E1 plus work is equal to E2. E1 is equal to 0. The work done is equal to minus mu k magd. Okay, and the energy at time 2 is equal to all of this. Okay, 1/2 ma va squared plus 1/2 mb vb squared plus 1/2 I omega squared minus mb gd. Okay, so how are we going to solve this? What we're trying to solve for is the final velocity of b at this later time after it's fallen a distance of d, right? B is going to fall a distance of d. How fast is it going when it gets there? So I have velocity in this term, I have velocity in this term, and I can note that the velocity of A is equal to the velocity of B, and I'll just call that V, because A and B are connected by a string. They have to have the same velocity here. So I have a velocity here, I have a velocity here. This term, I know everything. These are all knowns to me. This term, I know everything. These are all knowns to me. This term we have to deal with. Moment of inertia we presumably know. We'll just keep that as I. Omega is our angular velocity. Right? That's how much angle per second our pulley is spinning through. Right? Our pulley is going to be pulling through some amount of angle every second. Right? That's our angular velocity. And so we want to put this in terms of a linear velocity. Basically, if the string is wrapped around the pulley and the string is moving at the velocity of A and the velocity of B and the velocity of string should all have the same velocity, they're all connected, that means the edge of this pulley also has to be moving with that linear velocity. And we have an equation that relates linear velocity and angular velocity, and that is V is equal to omega r. Right, so if I know the angular velocity, if I want to write this in terms of the linear velocity, I just have to solve it for omega, and that's omega is V over r. Okay, so I'm going to replace this omega in this equation with V over r, and then this term, and this term will have a V in it. I can then factor that term V out and solve. Okay, so let's do that. And I'm also going to just move this term over to this side of the equation just to simplify things a little bit. Okay, and here I have a bunch of terms with velocity in them. And then I'm going to play that trick, 1/2 I, I'm sorry, I don't need the B there anymore, this is just velocity. And I'm going to replace my omega squared with V squared over R squared, right? Omega is equal to V over R, so omega squared is equal to V squared over R squared, okay? And now I can factor out a term V, and I'll multiply both sides by 2 just to make things a little simpler. So I have 2 times, and I have a G in both terms here, 2G, and actually I have a D in both terms too. So D times 2 times G, MB minus mu K MA is equal to, and now since I multiply both sides by 2, all these 1/2s go away, and I have a V squared in each term, so I can factor out that V squared, MA plus MB plus I over R squared. Okay, so now I just have to solve for V. You can probably see what the solution will be now. I'm just going to write it up here since I ran out of room. So V must then be equal to square root of 2GD, and that's this part here, times this, MB minus mu K MA, all divided by this term here. So here is my equation. This is my prediction for the velocity of B, or of A, or of the string, or of the edge of the pulley. They're all moving at the same velocity after B has fallen a distance D. Okay, so it's somewhat complicated, but we've really modeled the system fully here. We've taken friction into account, we've taken the moment of inertia of the pulley into account, and you can see the more friction there is, the slower the velocity is going to be. Right? The bigger our coefficient of kinetic friction, this is minus that, so this is going to be smaller, right? Or the bigger a moment of inertia, the bigger term in the denominator, the smaller the velocity. So if the really massive heavy pulley, the velocity is going to be smaller, right? If it's a 20-ton pulley, this thing is barely going to be moving, right? So we can kind of conceptually see that this equation makes sense, and we've fully model a system that we've done in lab. So it's a fun problem. So thank you.